All right, we had a lot of fun calculating the standard deviation and the variance and the average of data sets. But how can we use that to help ourselves think about data? We're already pretty familiar with the concept that, hey, standard deviation can kind of be used to evaluate how close our measurements are together. But it can also kind of help us compare two sets of data. For example, if we just look at the average ages of different groups of people, it looks like the average age of group 2 is much different from the average age of group 1. It also looks like the average age of group B is pretty close to the average age of group 2. Those are kind of factual statements that you can't argue with, right? Because we define average. The question is that a true representation of the groups? Remember, averages are the result of a data distribution. An average is going to do a better job representing a group of data when the distribution looks like that, as opposed to when it looks like that. Yes? Here, your average is going to be right here. So your average would have a very small distribution. Whereas over here, your average would have your data would have a very huge distribution, or a high variance versus a low variance. So even though you have averages for these groups of data, they may or may not represent the group of data accurately, or give you a true representation of that group of data. Another way to think about this, let's take a look at this set of data here. 70, 70, 80, 70, 80, 75, 80, 75, and 25. If we take the average of that set of data, let's take the average here, add them all together. 70 times, we've got 1, 2, 3 70s plus 3 80s, it looks like, plus 2 75s, plus a 25, and that gives us 625 as our total. How many sets of points of data do we have? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to divide by 9, and that gives us an average for our test scores of a 69.4. That is irrefutably the class average. However, does that really represent how the class did as a whole on the test? After all, what happens if I remove this outlying piece of data? If I remove this outlier and just take the average of this set, I add those together, I get 600. And now I'm dividing by 8 because I've removed that 25. So the average without that 25 is 75%. Which truly represents that set of data? Which truly is a better characterization of that set of data? Food for thought, yes? All right. So we have two possibilities or two sets of data here. We've got group A where we've got those test scores. Where their average is 75 and the average of the other groups is 69.4. Repeating. How close are they really together, though? Is this group really close to that group, or are they far apart? And this is where the variance or the standard deviation can help us categorize the groups further. This group is hugely influenced in the standard deviation and variance by that 25. The standard deviation for this group is plus or minus 17. The variance, hold on to your hats, the variance is a whopping plus or minus 264. Whereas for this group, the standard deviation is a measly 4.6 plus or minus. We'll call it plus or minus 5. And the variance is simply plus or minus 19. So there is a huge difference in the spread of these two groups. This spread can be really super important. Let's take a look at two other sets of competing data and some of the illusions or problems outliers like that 25 can cause. Okay. Here are the test scores from 3 different classes. When the professor looks at these test scores, the first thing he's going to do is he's going to take the average. And he takes the average and he discovers that Group A students scored 96.375. Group B had an average of 86 and Group C had an average of 78. So the question then becomes, is Group A a better class than Group B? Is Group B a better class than Group C? Can we say that? And a lot of you are saying, well, yeah. The averages are pretty clear. Group A must be better than Group B, and Group B must be a lot better than Group C. Are they really, though? Remember what Mark Twain said about lies, damn lies, and statistics. Let's take a look at our standard deviation. If we take a look at the standard deviation for each group, we see that there's a standard deviation of 96.3. So we got 96, and we'll say plus or minus, we'll round a little bit. So we'll say that my class A has an average of 96 plus or minus 2, meaning that the majority of my students are between 98 and 94 in terms of their grades. Over here, we have 86 for an average and a standard deviation again of 2. So we can say that we have a class average here of 86 plus or minus 2, meaning that our test score should be mainly between 88 and 84. Notice there is no overlap in these two groups, correct? So our classes are bunched up tight, in both group A and B, and there's no overlap in these two groups. So we can say, based on standard deviation, group A is a significantly better class than group B. We can take this a step further. Let's look at class C here. They have an average of 78. Look at their standard deviation. It's plus or minus 8. So we say we have a class average of 78 plus or minus 8, meaning that most of our grades are between most of our grades are between 86 and 70. On average, our grades range from 86 to 70. Look at that. This class's grade range overlaps with this class's grade range. Some of the students in Group C would have scored right in the middle or right in the average of Group B. Despite the fact that the classes have different averages, because of that overlap, we can't say that the group B group of students is really different than the group B. Yeah. Because those ranges overlap when we apply the standard deviation, we can't really say that group B is significantly different than group C. We can say however, that there's no overlap between group A and group C. So group A is significantly different from group B and group C. Now that's a good way of ballparking whether or not two groups are different. If we really want to drive home whether or not two groups of data are different, we could use the variance. And I'm going to clear things up a little bit here. Whoops. Clear off a lot of the clutter I wrote here. Okay, we have our variance here. What our variance does is our variance kind of tells us what our curve looks like. It gives us the shape, more or less, of that entire curve. So for this curve here, we've got 96, and our variance is, we'll say, 2.5. So the vast majority of our data is going to be between 98.5 and I'm subtracting 93.5. Vast majority of our data, we've got a variance of 3 here. The vast majority of our data here is going to be between 89 and 83. Over here, we've got a variance of 55, meaning the variance of our data statistically will be somewhere from I'm subtracting in my head, sorry, 23, and now I'm adding in my head, slow processes today, it's late, 133. I think I went off the screen there with my 3. So there's a much even larger overlap with this set of data and the others. Because of this variance in this class is so high, we can't really say that group A and C are different based on variance. We can when it comes to standard deviation, but not on variance. With variance, we can still say that group A and group B, however, are different. A lot to take in. Let's try to do this in terms of some pictures and represent what we're talking about with some pictures. Before we go on, though, would you write down quark? Everybody write down quark. Deep Space Nine is the best of all the Star Trek series. If you think otherwise, you're just wrong. Alright, let's take a look at that population data we were looking at the beginning and asking ourselves whether or not we could tell those two sets of data are different. Here's our group 1 and group 2 with average ages again. But this time, what they've done is they've introduced what are known as error bars. Error bars graphically display the variance. So these are called error bars. Graphically show your variance. In other words, how far your data is away from the average. And stock market people love these business majors, by the way. If there's a business major in here who's watching, this is something they love. You'll very rarely see a stock chart without error bars involved. Now, error bars are often given with something known as a confidence interval. And a confidence interval is the percentage of data that falls between the average plus or minus the variance. In other words, if we said that this error bar right here was measured at a 90% confidence interval, or is measured with 90% confidence, if we said it was measured with 90% confidence, that means that 90% of the data collected would have a value somewhere between, it looks like, 15 and 65. Most data published is published at either the 90 or 95% confidence interval. If we look at our confidence intervals with our two groups of populations here, clean things up a little bit. Oh, why don't you write down Odo? Everybody write down Odo. Back to our question about whether or not our group of students were different. Notice the average age of group 1 appears to be much less than the average age of group 2. But notice that there's a huge overlap here between their error bars. Because of that huge overlap, we can't really say that the two groups are different. They may be different, but we can't say it. Here, however, there's no overlap. Since there's no overlap in those interval bars, or those error bars, the two groups are different. If we looked at an actual scatter plot of the data, we could see what we're talking about. In group A and group B, everybody's close to the same age. So there's no overlap, and there's no overlap between the person with the lowest age in group B and the highest age in group A, or less than a 90% chance of an overlap. In group 1, they're all spread out. Their ages are all spread out. Same for group 2. So there's a huge overlap in the ages of those groups. So that's one of the reasons talking about standard deviation and talking about variance is important. In order to truly say to a given confidence level that two sets of data are different, their error bars shouldn't overlap. If the error bars do overlap, then it's up to debate how different those guys are. That's it for our introduction to statistics. What I want you to do now is, in addition to taking the pre-lab quiz, I want you to today do your graphing by hand. Please submit your graph by hand. Make sure you submit it in the digital Dropbox in class. And we'll go over computerized graphing in another lab. Beep.